In the previous videos, we discussed about two special properties of a scalar product of two vectors. In this video, we will discuss many more about properties of a scalar product. Let us begin. Let us begin. First of all, recall those two special cases that we discussed in the previous video. As we know that if a vector A and vector B are perpendicular to each other, then the angle between them is 90 degree. So here a scalar product of two perpendicular vectors. Suppose vector A and vector B are two perpendicular or orthogonal vectors. Then the angle between them is 90 degree. A vector dot B vector is equal to modulus of A vector modulus of B vector modulus of B vector cos 90 degree. As we know that the cos 90 degree is 0 and modulus of A vector modulus of B vector times 0 is equal to 0. So if a scalar product of two vector is 0, then they are perpendicular or orthogonal vectors. As in the figure here, here is one vector, say A vector, which is shown in the figure, and the another is B vector, and the angle between this A vector and B vector is 90 degree. So their dot product is 0. So in conclusion, we can say that if the dot product of any two vector is 0, then angle between them is 90 degree and is 90. Now, as we know that if a vector A and vector B are parallel to each other, then the angle between them is 0 or 0 degree or 180 degree. As we know that two vectors are said to be like, we know that and two vectors are said to be like if they have the same direction and unlike if they have the opposite direction. So let's look at like vectors. A scalar product of two vectors, say a vector A and vector B are two like parallel vectors, then the angle between them is 0 degree. By the definition of the scalar product, A vector dot B vector is equal to modulus of A vector dot modulus of B vector cos theta, and so here theta is 0 degree. So as we know that the cos 0 degree is 1, value of cos 0 degree is 1, so times AB times 1 is equal to AB vector, and the second one is a scalar product of two unlike vectors. Let a vector A and vector B are two unlike parallel vectors, then the angle between them is 180 degree. Since they are unlike, so the angle between them is 180 degree. By the definition of a scalar product, A vector dot B vector is equal to modulus of A vector cos 180 degree is equal to AB times minus 1. Cos 180 degree value is minus 1 is equal to minus modulus of A vector modulus of B vector. Now let us see the magnitude and the direction of any vector. Say a vector, we have a vector and their components are given in ij form. X1 is the x component and y1 is the x component and y1 is the y component, and it is written in the form of ij. As we know, I is the unit vector along with the x-axis and j vector is unit vector along with y-axis. So this ij form can be written as x1 y1 in column form. For magnitude, modulus of a vector is equal to root over x1 square plus y1 square is equal to root over coefficient of I vector whole square plus coefficient of j vector whole square. And for the direction, to get the direction from is tan theta is equal to y1 by x1, that is coefficient of j vector by coefficient of I vector is equal to y component by x component. Next one is length of a vector as a scalar product. Length of a vector. So here we are going to find the length of a vector as a scalar product. Let us see. Suppose a vector has the components a1 and a2. That is x component as a1 and y component as a2. Be a vector, then a vector dot b vector is equal to a1 a2 times again a1 a2, and a1 is multiplied with a1 a1 plus a2 a2, and this is the definition of a scalar product of two vectors. In alternative method we have discussed a1 a2, that is x1 x2 plus y1 y2 in the previous video. So now a1 a1 square plus a2 square is equal to simply a square, as we know that in Pythagoras relation we know that the h square is equal to p square plus b square. So therefore a is equal to root over vector a dot vector a. Hence the length of the vector a is the positive square root of a scalar product a vector a product. The scalar product of a vector with itself is often written as the square of the vectors a vector dot b vector is equal to a vector a square, and simply we can write a square. Now the unit vector in the direction of a vector. Unit vector of any vector in the direction of the same vector. That is, let a vector has the x component as a1 and a2 as y component, and it is written in the form of ij be a vector. Then the unit vector in the direction of a vector is given by a cap. This one is called the cap, this one is called the cap, this one is called the cap. So a cap is equal to vector a by upon modulus of a vector is equal to a1 I vector plus a2 j vector by root over a1 square plus a2 square. Now here are the properties of a scalar product of two vectors. Number one, the scalar product of is vector two vectors is commutative. That is, a vector dot b vector can be written as b vector dot a vector. The second one is the scalar product of vectors in distributive over vector addition. That is, a vector dot in bracket b vector plus c vector is equal to, now we have to multiply with b, a vector dot b vector and a with c, that is plus a vector dot c vector. And the third one is the vector the two vectors vector a and vector b are perpendicular, then the scalar product of a vector and vector b is 0, that is, a vector dot b vector is 0. And is, if a vector dot b vector is 0, then orthogonal, that is, they are perpendicular. If the dot product of any two vector is 0, then they are orthogonal. If a vector dot b vector is equal to modulus of a vector modulus of a vector modulus of b vector, then the vectors a vector and b vector are like vectors. A vector and b vector are like vectors. If a vector dot b vector is equal to minus a modulus of a vector modulus of b vector, then the vectors vector a and vector b are unlike parallel. A vector dot b vector is equal to vector a square is equal to, simply we can write a square. And here, if vector I and vector j are unit vectors in the direction of x-axis and y-axis respectively, then I vector dot j vector is equal to 0, j vector dot I vector is equal to 0, I vector dot I vector is equal to 1, j vector dot j vector is equal to 1. And let's learn about the some simple identities. And the simple identity are a vector plus b vector whole square is equal to vector a square plus 2 a vector dot b vector plus b vector square is equal to, simply we can write a square plus 2a vector dot b vector plus b square. And similarly, a minus vector b whole square is equal to a square minus 2a vector a dot vector b plus b square. A vector dot a vector plus b vector dot a vector minus b vector, simply we can write a square minus b square. This helps while doing the problems related with the scalar product of two vectors.